experiment. We're going to, okay. Alright, so who has started doing a little bit of work on some of the geometric proofs from last bit and exploring some of them? We're also, I'd like you guys to, what we're going to do is reinvigorate the use of our Google Classroom for our work now on differentiation as well as the geometric proof. So where you've been able to work on just that small handful there of exercises, and if you need assistance with them, we can do some at our homework club. And once they're done, could you please click that you're done, that they're complete, and either show me in person in class that you've done it, or you can take a photo of it and post them up onto the Google Classroom like we've done in the past, okay? So we're going to reinvigorate that and then continue on with our work with our differentiation. So after today, I'd like us to be doing 7.2 and then 7.3. So that's the set of homework that I'd like you to do this week and over the weekend for next week, please. So today's lesson, we're exploring, we're going to define, I'd like to introduce to you, and you practice the derivative of what's called the hyperbolic circular function. And then we're going to apply some derivatives by finding tangent lines and normal lines, the different curves. Okay. Alright, so looking at what we've done previously, let's try. I'd like us to draw on what we remember from last class on the derivatives of the sec and the cosec and the cot. And we're going to use that to differentiate these functions. Now, this is just not any normal sec function, it's an x multiplied by a sec function. So what technique should we be using? A product rule. Yep. Okay, and as you can see, we've got a product of two parts, a u function multiplied by a v function. So we define each part. What are we going to write as for the u function?
X times sec.
Well, you have to recognize the two parts that are multiplying and make one of the part u and the other part v. We can say let u is equal to x. And then the derivative, u dash, is the number 1. Okay? And then the other function, v, sec of 2x. Now who can tell me from last class what's the derivative of sec? 2 tan sec 2x. Okay? So it's a tan sec. Derivative of a sec is a tan sec. Okay? Good. So you get your parts, you apply the derivative to each, and then therefore we put them together. dy dx is equal to the u function multiplied by v dash plus u dash multiplied by v there a way we could factorize? Sec 2x is a common factor. So you can look for common factors. Okay, in this case, the sec function is that common factor, and then we've got a 2x tan 2x plus 1. Okay? And there we have it. Does that make sense? Alright. Good. So now let's try this one. Determine the general solutions for stationary points of the function. Right, so we have to draw on a number of things here. First thing is finding stationary points of a function. Okay, what's the method for that? That's correct. The derivative dy dx is equal to 0. And we set up an equation that we're going to solve. Okay, and then whatever that equation becomes, we have to identify, well, what's going to be our general solution for the circular function we're looking at. Okay. And what kind of differentiation technique? Do we need to do anything in particular, like a product rule or a chain rule or a quotient rule? If we know what the derivative of cosec is, then we can apply just that shortcut rule as it is. If you've got it summarized for yourself in your summary notes, and you can look it up, then you can apply it straight away. So the derivative of the whole function is the derivative of each separately. Okay? So we take the derivative of the cot, of x, and then we subtract. And even though we've got a factor of 2 in front of the other function, the 2 itself is just an extra factor that won't change or be manipulated in the process of differentiation. Yeah? So it's just, it can just stay as a multiplying factor. Factor 2, that can not take part in the process of differentiation, and you can express it like this. Okay, so the derivative of the whole lot is the derivative of each term excluding those extra factors. Okay? Alright, what do we remember about the derivative of cot? Say again? Yes, negative cosec squared. That's the one. So derivative of cot becomes a negative cosec all squared. Okay. Minus 2 lots of. Now the derivative of cosec. So it's a minus cot of x cosec. Okay, those were the equivalence what we established last lesson. All right, let's tidy it up. So this one stays. One's going to stay the negative. Now this negative of the negative, that goes positive. Okay, and stationary points is when the derivative is equal to 0. We get this, we set up our circular function equation. Yep.
Are we expanding the negative 2 out to each? The negative 2 out to negative cos?
Okay.
Or are they
Yep. So this term here, the cosec, that's just one term because it's a multiplication of the both parts. So when we expanding, you only expand to addition or subtraction of terms. Yeah? But being the one term, it's just now a factor of 2 in the front. Okay. Alright, so now we start thinking about how we're going to solve this equation. So, first thing is, can we collect terms in a way that allows us to employ the null factor theorem? And that's very advantageous to consider because we've got the equation equal to 0. When something is equal to 0, we need then two factors that multiply that equal to 0, and then we can use null factor theorem. Yes, so you can see it's that cosec, can't you? Cosec times, take out that common factor, and now we've got a negative cosec and plus a 2 cot of x is equal to 0. Therefore, we can say, using null factor law, well, we've got cosec of x has to equal to 0. And, second part, negative cosec of x plus 2 cot of x is equal to 0. And now two parts. And then that allows us to go ahead and we can solve them separately. Okay? All right. Now, how am I going to expand this? All right. So the first part, let's look at the cosec x is equal to 0. Okay, now what's cosec by definition the same as? 1 on sine. Okay, good. Now, we have a situation, we have, okay, when does the cosec of x equal to 0, or when does 1 on sine go to 0? Alright, now, if 1 on sine is equal to 0, that means, what about the denominator? What should sine have, or go to, for the reciprocal to equal 0? You can't, can you? No, very good, you can't. You can't. It is undefined. Yep. Okay? That is undefined. So by definition, that cosec, it actually never equals 0. And if you're saying, well, 1 on sine, does that go to 0? Well, that only occurs when sine approaches infinity. Does sine ever exponentially increase to infinity? No, because it's bound within, its amplitude. And you can see there the value will never go up to infinity because it always turns and goes back down to 0. Yeah? So that's undefined. Okay? And thinking about it in terms of cosec, okay, there's a little graph of cosec. You can see, again, that never goes to 0 because as it gets closer to the axis y equals 0, it turns and then goes up again. Alright? So this factor doesn't equal 0. It doesn't contribute to 0. So there's no solutions of x from the cosec factor. Okay? What about the other factor? Now, what was the other factor? I can't remember.
Negative cosec x plus 2 cot x.
Negative cosec
X
of x
plus 2 cot x.
plus 2 cot of 2x?
Of just x.
Yep. Now, let's have a look at this one equaling to 0. Yes, very good. Rearrange it. Let's add the cosec to the other side. So we're going to have a 2 cot of x is equal to cosec of x. Okay? Now, think about what we've done by doing so. We can say what? Well, cot is cos over sine. Cosec is 1 on sine. We've still got that factor of 2 there. Good. Okay.
If you multiply the sine to the other side, will the sines cancel out?
The signs could cancel out, but I want you to think about dividing out, cancelling out a whole factor of sine of x. Okay, is essentially removing that whole part of the equation completely. All right, you have situations where, what about for a certain x value, the sine of x ends up having a result of 0. Then you're going through the process of cancelling out this factor through division that could in fact have a value of 0, which is undefined. Okay, and cancelling out factors of sine and cosine for which x has relevant solutions, it removes the chance of finding solutions from that part of the equation. Okay? So this part here, this kind of rearrangement can lead to the idea of, okay, I've got extra factors I want to cancel out. Okay, and rearranging like that leads to wrong solutions or incomplete solutions. Okay? Because then if I cancel out sine of x, and that just means, oh, the cos of x is equal to 0. Now cos of x is equal to 0 is a completely different equation than negative cosec of x plus 2 cot is equal to 0. Okay? We've lost all the information we're going to get from the factor of sine x. So keeping it in the first line, then we can see the cosec is a 1 on sine x plus, and the cot is a cos of x on sine x. Well, that is equal to 0. Okay. Oh, forgot the factor of 2. Thank you. Okay. Now retaining that, then we see, all right, we've got this common factor of 1 on sine. Okay. We'll keep that bit. Now we'll end up with a negative 1 plus 2 cos of x. Well, then that goes to 0. Okay. And then again we use null factor law. Yeah. Now, what can we see? Do we get 1 on sine? equaling 0?
No.
No. Okay. But, so that means the bracket, -1 plus 2 cos of that can equal 0. So, even though in this case we can see that the sine part of this equation, again, is not leading to real solutions for x. Okay, so Josh, what were you saying about we could cancel out the signs? For this particular example, that may have been okay, but it's not good practice to adopt that thinking. Okay, the better practice is to break down your reciprocal circular functions like so, then collect common factors, okay, then use null factor law. Alright, that way we can see the part that is equal to 0 using null factor law, and we can make a decision whether that is correct, if that is true or not, if we do get solutions from that. Okay? That way we're interpreting and thinking about the information that the one on sine equaling to 0 can give us. Alright, in this case we know that it can't equal 0. Yes, Josh?
We ultimately got to rearrange the cos. So it's
Yes.
cos of half.
Precisely right. And then that's now where we're going to get all our solution from. So therefore we're going to get cos of x is equal to 1/2. Okay? And so now we're up to the point where we can say, well, x is going to equal to the inverse cos of 1/2. Taking the inverse on the other side. But you have to keep in mind that's only part of the possible answer. We're after a general solution. Yep. So who remembers the general solution rule for cos? Yep. Very good. 2 by some counter, we could use n or k. Pi. Plus or minus? Both? Yep. There we go. Plus or minus the inverse cos of that number. Okay? And there we have it. And then from there, we can tidy that up a little bit. Now, can we evaluate the inverse cos of 1/2? Pi on 3. Very good. And now we just get a common denominator. So we're going to have a 6n plus or minus 1 multiples of pi on 3. Okay, and that's for our n being whole integers. So the work on forming general solutions to solving circular functions, we're going to do a lot more work in methods, so you can draw on that as revision and on to consolidate and build that your understanding of that idea and to practice as well. Okay? So importance there is knowing the derivatives of your reciprocal circular functions, and then practice of solving these circular function equations. Okay? And the idea is to factorize and then use null factor theorem to get your solution, instead of cancelling out common factors of circular functions. Any questions, please? Okay? Alright, so we're going to introduce this, we're going to study this very interesting curve. This is a naturally occurring curve. And I want you to look at the different diagrams and you see how it occurs and when it's used. It's like, it looks like a parabola, doesn't it? However, it's not a parabola. So the occurrence of that curve is different to the parabola. The situation of the parabola is motion under the force of gravity, okay? Such as a projectile like we're kicking a ball through the air, where the only force acting on it is the force due to gravity pulling it down, then that experience goes through a parabolic path, okay? So that is what you get, where you've got one object with one amount of mass. But where you get linked objects, all connected together, and each part of the objects that are all linked have their own masses. So there's a mass distribution across the whole object, and that, under gravity, forms this shape. Such as a chain. This chain is, you might say, well, that looks parabolic, but every ring of the chain has its own mass. Okay? And every ring of the chain is experiencing the force pulling down towards the ground due to gravity. And so you've got the weight force, every point pulling down, and it produces this shape. And it's called a catenary. It's called a catenary. That's the curve. So a catenary is the shape of a perfectly flexible chain suspended by its ends and acted on by gravity. Josh?
What do you mean by the term perfectly suspended?
What do you mean by perfectly suspended?
Perfectly
Well,
flexible.
it's pinned, like this is beads on a string. So it's pinned there, pinned there. The whole lot allows to freely be at rest under gravity with no other force pushing against it in a different direction.
So would a string be classified as a catenary? Or
Yes, string. Yep, absolutely.
Or is it one?
Yeah, it's one continuous object all linked together, but every little bit of the string has a distribution of mass along the whole string. Okay, yeah, particles. Okay. Now, as soon as, and what man had discovered was that if you take this shape and you invert it, okay, then you get a very, very solid and strong structure. It's called an arc. Okay, it's an inverted catenary. And the inverted catenary, or arc, is the most stable architectural construction that you can form.
I thought a triangle was.
Sure. But I'd like, what I'm going to do is, where I come from in Blackwood, but during the gold rush, it was a mining location, and all the miners came and fielded that spot. And if you walk around the forest of Blackwood, you've got two types of shafts. You've got a shaft, that mine shaft that goes into the ground that looks like this. Okay? And then you've got a mine shaft that goes into the ground that looks like that. Now, the British built this shaft, whereas the Chinese built that shaft.
Always smarter.
Alright? There aren't many of these still standing. In fact, the only ones that are standing are the ones that have been preserved for historical purposes and they've been reinforced. Okay? Because they're not stable and they've all fallen down. Whereas this one, the Chinese mine shaft, they're all still standing strong and there's no concern for them collapsing at all. Okay? The Chinese knew about the inverted catenary as the most stable construction, and so when they came, they all built their mine shafts with the arc shape. Okay, even the spider knows about the strength of the catenary. So you can see it forms that same shape. Okay, so that's the equation. Make sure you write that down. It's the sum of two exponentials, an exponential function plus an exponential function that's been reflected, and then divide by 2.
That's what a triangle is in this
Now, okay, so if you have this factor A in it, essentially it's a weighted catenary such that it's all scaled appropriately. And the points from where it hangs there are like real points for which you can just flex. And if you grab it there and pull it out, then the thing drapes down more appropriately. You can imagine out here, fixing it there, so it breaks like that. So that's what the factor of A in that position is doing, that transformation. All right. So, giving that, now there's our equation. So we're going to examine this graph on the CAS. We can define it in the CAS, like so. So it's defined. Now, I just want to fiddle with the equation a little bit, and there's the function now. Hit enter. I get that. Yeah. So, by definition, the catenary curve that is expressed like this is a hyperbolic circular function. It's called the Cosh function. Okay? It's the Cosh function. And it defines, in fact, all three. You've got a sine, a cosh, and a than function. Sine, cosh, than. That's correct. Sine, cosh, and than. Okay, so there they are. So what I'd like you to do is just define that for yourself, write them down. And the graph. Now, fortunately, you don't need to know and be able to sketch these by a hand for this course. So the only thing we're going to learn and practice today is the definition, such that if you see a function that looks like this, okay, then it's equivalent to the cosh of x. Only because the CAS, okay, will always transform an exponential function of this structure into its hyperbolic circular function equivalent.
So there's still an A at the front normally?
No. This is, your standard blank, boring variety of your, cosh function.
So was the one with the A out the front, was
Yep.
that like a general?
That one was transformed specifically for a reason to copy the real situation where you get like the chain held at 2 points, and if you bring them closer together by changing your A, then the curve does this. If you pull them further apart by changing your A, then it breaks like that. Does that make sense? Yep. Alright, so as you can see, the addition of your exponentials is the cosh. The same exponentials, but then you subtract them. That's the sine. And then than is a sine divided cosh. Okay? Just like normal tan definition. So it's the subtraction of the exponentials divided the addition of the exponentials.
And you call it shine.
Shine.
English teachers would hate it.
So it's, in terms of pronunciation, you can say hyperbolic cos, hyperbolic sine, hyperbolic tan. That's okay. But for short, the nicknames cosh,
Josh is the one there.
No, than.
Josh is Josh.
so it's shin, but we say shine because the shine function sounds better than the shin function. And then it's the than function. Okay, does that make sense?
You got some cosh on you? You have any cosh?
Just stop trying to shout some gosh, really? Dear man. Okay. Now, an important thing I'd like you to keep in mind, this guy is going to pop up in the future when we study mechanics, and it will be used to model the motion of an object falling under quadratic air resistance.
Quadratic.
Yep. Your half pack.
Oh, okay.
Half pack V squared. Yeah?
We did this in physics, yeah.
Lovely.
So
But we don't actually have to do the maths. Yeah, I was gonna say.
Okay? So you'll learn how to come up with your velocity function and your displacement function for quadratic air resistance with your half pack and your force in there. All right. Has everyone got that noted in your books? So it's just rough, the name, the definition of the function. Okay, so the sketch, don't worry about too much. Just be, roughly familiar with the shape. But what we're going to do is practice differentiating those functions. Ready? We're going to... Let's have a go. We'll come back to that shortly. Now, so essentially when you're differentiating these exponential functions, okay, you treat it normally like we did. Okay, so the derivative of this kind of function, see you've got your factor of a half. The factor of a half is that extra factor that doesn't take part in the process itself. So you can have that as a factor of half on the outside, and then we're just differentiating the sum of the two parts, the e to the 2x plus e to the negative 2x. Okay? No, this is two separate exponential functions that are simply adding. So the derivative of that becomes, with that factor of a half, it's the derivative of the first function plus the derivative of the second function. Okay, so you just differentiate each exponential part separately. Alright, so e to the 2x becomes its derivative 2 e to the 2x. Okay, e to the negative 2x, the negative comes out the front and becomes negative 2 e to negative 2x. Okay, so now we've got this common factor of 2 there that comes out, and we've got the e to the 2x minus e to the negative 2x with this, still that factor of a half that we took out because it didn't take part in the process. And so we end up with this as the derivative. Now, by definition, what is this fraction equivalent to? Not cosh, shine. So there you go. The derivative of a cosh being this one, this is in fact, if you check your definitions, that is a cosh. The derivative of a cosh function is a shine function.
It's not your regular, all the sign.
Yep. That's correct. It behaves very much like a regular sine, cos and tan. Whereas this is, because of the 2 there, this is a cosh 2x. Okay? So the cosh 2x, the 2 in the cosh function, comes out as a factor. And I forgot the 2 there, that's better. The factor of 2 comes out, multiplies out the front, and then the derivative of cosh goes to a shine. Okay? So, what's the normal derivative of cos? Sine. Yep. Derivative of cos is sine. Derivative of a cosh is a shine. Kind of makes sense. Now, what's this function? That's the shine. That's a shine of 2x. Okay? That's what that's equivalent to. Now, let's differentiate it similar to what we did before. Who'd like to predict what should we get? Negative cosh? Yeah? Good hypothesis. Let's put it to the test. Okay, so the half can come out. We don't have to differentiate that. We're going to differentiate the exponential part only. Okay. So we've got a 2e to the 2x, and then they've already got a negative there, and that's times by the negative 2, so it becomes a positive 2e to the negative 2x. All on 2. Don't cancel out your factors of 2, because if we take out that top factor of 2, it will be 2 times this. And by definition, what is this fraction the same as? That's a cosh. That's correct. So it's a 2 cosh of 2x without the negative. So it's a positive. Slightly different than normal derivative of sine. Derivative of sine is a negative cos, whereas derivative of a sine, hyperbolic sine, is positive cos, cosh. Okay. Now, let's try this. What kind of technique should we use to differentiate this one? Quotient rule, very good, because we've got, overall a function divide another function. Alright, so this is, by definition, a fan function. Let's try out quotient rule. Okay, y equals u on v. So, let u is equal to e to the 2x plus e to the negative 2x. Then u dash, differentiate both terms separately. Derivative of the first one, 2e to the 2x. Yep, and then negative 2e to the 2x. Okay? Negative. Yep. Does that make sense? Now, what about the denominator? V is equal to an e to the 2x minus e to the negative 2x, and its derivative. So the 2 comes out the front, 2e to the 2x plus, okay, the negative 2 times the negative. Understand? Okay. Now, we've got our parts, therefore let's put them together. Who remembers the quotient rule? What comes first? V, good. V dot u dash. Then minus, good. U, we've already got a u dash, so this one is just the u. V dash. Okay? Alright, now grab your parts and let's substitute them into the formula. Got to use brackets so you keep everything together. So it's a v function, e to the 2x minus e to the negative 2x, which is a bracket multiplied our 2 e to the 2x minus 2 e to the negative 2x. Okay, there's the first double bracket, and then that is subtract. Next bit, u times v dash negative 2x. Okay. And then all that is on our v squared. E to the 2x minus e to the negative 2x all squared. Alright, so you've got a nice expression there that you have to work out simplifying. So think about what you have to do. We've got this, you've got in one bracket, you've got this common factor of 2, yeah? So that common factor of 2, to make it a little easy for yourself, you just factorize that and bring that out, okay? Same with this one down here, this bracket, that also has a common factor of 2. So you take that common factor of 2 and factorize it out and bring it out, okay? Does that make sense? And you end up having this common factor of 2 in both the terms, in the first double bracket term and in the second double bracket term. You take out that whole common factor of 2 outside the big red square brackets. Okay, so you can write a 2 out here and you don't have to write those 2's there. That's the first little thing you can do. And then you go ahead and perform your double bracket expansions. Does that make sense? Yeah. Beautiful. Alright. I'm going to leave that as a little exercise for you guys. Okay? To try yourself. And next class, I'd like you guys to tell me, what do you think that's equivalent to?
You get something cancelling to shine.
You might get some things cancelling out. Oh, but it's going to be your little exercise. Now, how are we doing for time?
Hard up, please.
You've got 10 minutes.
It's going to be equal to shine.
Alright. You can have a predict where you think it might be, but try it at home, please.
So you do this.
So we're going to try a few more different examples of functions that we're going to practice differentiating, and then try and apply them to different things. Okay. Now the first idea, once you differentiate all these different types of functions using your product rule, your chain rule, your quotient rule, we want to use the gradient function we get in different ways, okay, like finding stationary points. Then we're going to learn about things like trying to identify what is the equation of a tangent line to a curve, and then what's called a normal line. Okay, and then we can apply it in further situations after that. So the first thing, tangent lines. A tangent line can be determined at any point. So here's a cot graph. There's, at some point, we've got a tangent to the curve. Okay? And when we find the equation of a tangent line, we're going to follow a few steps. The first step is to differentiate your function. Okay? So the derivative of your function, being this part here, okay, we're interested in using that derivative and evaluating at a particular point, okay? The point where the tangent's at, because that gives you your gradient. What's the gradient or steepness of the curve? Yeah? So that's the second step. We substitute the x equals a point, where the tangent is at, into the gradient function, and you get your m number. Okay, you get your, essentially, the gradient of your y equals mx plus c, the gradient of your tangent line. Okay? So it's very, very important to make that connection. If I'm trying to get an equation of our tangent, this part, then the gradient of the straight line is given by this. The derivative evaluated at a point. Okay. Then the other important thing we have to do is then take our x number and substitute it back into the original function, f of x, because we're after the y coordinate. What is the corresponding y value? So we get both a complete coordinate, an x and a y. Okay? The x is the point given to you, whereas the y is evaluated at the original function. And then all that working out, all that information goes into this rule, the formula, y equals m times x minus x1 plus y1 to get your straight line. Find the equation of the tangent to cot at pi on 2. That's not going to be too interesting. Let's do it at pi on 4. What's wrong with pi on 2? Cot is 1 on tan. What happens at tan on pi on 2? Undefined. Yeah. Let's avoid that. Alright, so let's say pi on 4. So first, we differentiate dy dx. Okay, derivative of the cot gives us, who remembers?
Negative k cosec, so it's just negative cosec squared.
Yep. Hi Josh. Where's you been? He's gone. Yeah. Yeah, I'm not putting up this shit.
Sees culture starts this one.
Hi Josh. Hi Josh. Hi Josh. I've managed all three on your second entrance. You alright, mate?
Yep, I'm fine.
Alright, cool. Alright, so then at that pi on 4 value, what's going to be our gradient number? So negative cosec squared of a pi on 4. Okay? You can put it in the calculator, of course. But you can also think about it as, in terms of the reciprocal, cosec is the same as sine. Okay? Sine pi on 4. Who remembers? Root 2 on 2. Good. So you've got to square it and do the reciprocal. 2. 2. Yep. Good. Square and do reciprocal and get whole number 2. Okay? And you end up with negative 2. Alright, so then there's your gradient number. We now have to substitute back into the original function, back into y equals cot. Okay? And then use that. So we'll just take that up here. So what is f at pi on 4? Which is cot on pi on 4. Tan, who remembers what's tan? Tan of pi on 4? 1. So cot of pi on 4 must be 1. That's right, 1 divided 1. Okay, so from that we're getting a coordinate pi on 4 and 1 as your xy coordinate. So the tangent occurs at that coordinate point. Okay, and to finish it off, y equals to mx minus x1 plus y1. Okay, so it's a negative 2 bracket x minus your pi on 4 plus your y1 plus 1. Okay, and you can expand and simplify and get your result. So you've got a negative 2x and a plus pi on 2 plus 1, as that part there, the pi on 2 plus 1, is your y-intercept as a whole number. And it's a mixed number. You've got a radian together with a whole integer. Okay, so you can just keep it together in brackets. Okay, so it's that kind of approach to determining your tangents. Okay? Does everyone make sense of the steps? Beautiful. So, what do you think the normal line is? What's the normal force? Josh?
Oh no, it's pointing up.
Yep, up. How do we describe it?
Perpendicular?
Perpendicular, very good. Perpendicular to a plane or a line. So the normal line coming off a curve comes out perpendicular off the tangent. Okay?
What does that help us with?
So by definition, here, a perpendicular, a normal line is, if that's your tangent there, then the normal line is this one that's coming off at pi on 2 radians or 90 degrees. And the other thing that you have to do to your steps, which we'll practice next lesson, is use this rule to get the perpendicular gradient. Okay? Which we looked at in mathematics. Yeah? And that's the only extra thing we have to do to get a normal line. Okay.